Okay, kids, we're live.
My Twitter is golden.
You talk to other people. Why isn't it working? Because I have to calibrate. That is why. Yes, it's recording, and it's recording me calibrating.
That's awesome. We should say something.
And this is a demonstration of how this is using technology in the classroom. Is it working now?
Working now?
Working?
Let's try not to disrupt everyone. No.
Well, I'm learning.
Well, you're learning.
I'm learning.
You're learning us.
I'm learning you real good. Y'all don't work today.
Just walk out.
Are you done?
I'm leaving. I was fine.
Let us record that Dakota left the classroom.
Wow.
Coach, C-O-A.
Whoa.
No, I'm settle down.
Are you gonna play this like what's that?
I'm not gonna play it. I'm just gonna give them the YouTube link and they can go find it if they need to. I can't find it. Chapter 10. It's all about 3D shapes. So we talked about in chapter 9, we were just doing 2 dimensions, length and width, 2-dimensional shapes. Now we're talking about 3D shapes. So we are starting on the note paper that's just the front and back. Please don't be that kid who's on the 4-sheet one, even though I've already said twice now that we're doing the front and back paper. That happened in second period. Yeah, 3D shapes. So, 3D shapes. We know about these guys. They've got faces, which are the flat parts. They've got edges, which are the line segment parts. And then they've got vertices, which are the corners. So that gets filled in on paper. Okay, so, what? Oh, there you go. So, there's 5 different kinds of shapes we're going to learn about, but we're not going to get to spheres until like next week or the week after. So we're going to start with the prisms, the cylinders, the pyramids, and the cones. And the main thing that you don't already know is the difference between a prism and a pyramid. So, this yellow guy here is a triangular prism. And why is it a prism? It's a triangular prism because it has 2 triangles that are parallel to each other. And then this red guy is a triangular pyramid. Why is he a pyramid? Because it has a triangle on the bottom, and across from the triangle is a point, or a vertex. Right? And then cylinders are like circular prisms with 2 parallel circles. And then cones are like circular pyramids with a circle and then a point at the top. And the little parallel guys, the 2 triangles or the 2 circles, those are called the bases, and that gets important next week. So these are the different kinds. I mean, you can have, in terms of prisms and pyramids, any polygon can be made into a prism or a pyramid. Prism, again, has 2 parallel shapes, so this one has 2 parallel triangles, and a pyramid has just 1. So prisms always have 2 bases, and then pyramids just have 1 base. And I will let you fill all these in. Okay, if you're not done filling in, you'll be able to guess yourself what the rest of these words are. Okay, so on this one, we're going to do two things. We're going to classify the figure. So classify means from those things that you just filled in on the last slide. Zach, which one of these would you say that looks like? It is a prism. Which kind of prism? Triangular, rectangular? It is. So classifying would be saying that this is a rectangular prism. Okay? And now we're going to name the vertices, the edges, and the bases. So vertices, edges, and the bases. Vertices are just points, so they're just named with one letter. So for example, this angle here, this vertex is A, and that's all it is, it's A. So Gabriel, why don't you get all the rest of the vertices for me? Just name them out.
A, B, C, D, F, G, H, E.
Correct. Okay. So there's all the vertices. Edges are little line segments, so they're named with two letters, so I'll start. A, B, you know that would be like one of the edges. Okay, Ivana, you get three more. Okay, BC. What else? CD. And AD, okay? All right, let's get somebody else involved. Nancy, you give me four more. EF. Huh? FG. GH. And EH. Okay, Luis Morales, you get the last four.
BF,
BF. Okay.
BC,
EG.
BH,
BH. And AE. Okay. For the last one, they asked us to name the bases on a rectangular prism. All the sides across from each other are parallel, so anybody can be the base. But for our purposes, we'll say the top and the bottom. So I'll name the first base A, B, C, D. So Dakota, that would make the other base be correct. E, F, G, H. Very nice. So that's what it means to name the vertices, edges, and the base. Again, skip that one because it's not on your notes. Okay, a net is if you take a shape and like a little cereal box. Okay. It's okay. Okay. A net is like if you take a shape, and you know how like you're supposed to, nobody does. You're supposed to break down the cereal boxes before you put them in the garbage can or the recycling? No. You're supposed to, nobody does it. I don't either. I just mash them down and then shove them in there. But anyway. What? I mash them in there!
It's going to be exciting recording.
Well, we gotta make them watch. So a net is if you unfold the shape like that. So there's like a net, okay? Okay, so what shape would we make from this net? A cube. Or since it doesn't have tick marks to indicate that all the sides are the same, we'll call it a rectangular prism. This is like the only time that I'm funny. I'm not funny in real life.
No.
This is a real life.
Am I asleep?
You know that nobody considers school real life. Come on.
We have the real world in it.
Because this isn't the whole world.
What shape would be made from this net?
Cone.
A cone, yeah. This circle folds in, and then the other thing folds around, and it makes a cone. Okay, so that's a cone. The next two aren't on the slides, they're on your paper though. What's this shape going to make? A triangular pyramid. There's the triangle, and then that's the base, and then these little points on the triangles are going to form the point of the pyramid, so triangular pyramid. And then the last one, right, these two circles fold in, that rectangle folds all the way around, and it makes a cylinder. Super. A cross section is if you slice something, what's the shape of the place where the knife went through. So here's my rectangular pyramid, okay? If I were to slice this pyramid just horizontally, the shape of the cut that it makes is a square. Okay, so the cross section is a square. You don't worry about any of the 3D stuff in the background. You just worry about the shape of the cut, and it's a square. If I slice it diagonally, the shape of the cut would be a trapezoid. So the cross section is a trapezoid. Okay, so cross section just means the shape of the cut that you made with your proverbial knife. So if I slice off the tip of a cone, what shape is the cross section? Circle. Either a circle or a dot, depending on how you see things. Okay. Have I spoken to you about the American workplace?
Oh, no, please, Japanese.
The Japanese people can sleep because that's considered honorable, but the Americans don't. No, this is not a hexagon. That's a shape of cross section. Pentagon, yeah, 1, 2, 3, 4, 5. That's a pentagon cross section. And we don't have anything else. That's the end of the first notes page. Does anybody have any questions?
There were 2 more on this.
4 more notes. Okay? Oh. So now we're on the quad sheet, the one that folds up. Remember polygons? Remember we talked about polygons, and polygons were straight-sided shapes, and we were talking about those like in chapter 7, and then we talked about them again in chapter 9. Now if you're in 3D, figures with straight edges are called polyhedrons. So that's the word that you fill in at the top. These guys here, these are polyhedrons because they have straight edges. And these guys over here are not polyhedrons because, as you can see, they got little curvy parts. Now, the next sentence on your paper is there is a special relationship between the number of vertices, the number of edges, and the number of faces that a polyhedron has. If you take the number of vertices and you minus the number of edges and you add it to the number of faces, it always comes out to 2 no matter what. Which is kind of neat. So let me prove that to you. Okay, everybody who's in this column, you're only assigned to the purple pyramid. Count the number of vertices, the number of edges, and the number of faces. Everybody in the middle column, you're assigned to this green hexagon prism. Count the number of vertices, the number of edges, and the number of faces. And everybody in the last column are assigned to this thing, which does not have a name, but count the vertices, edges, and faces. Only do the shape that you are assigned to, okay? Because if you try to do more than that, you're going to get bogged down in work. Okay, people in this column, what did we get for the purple pyramid? How many vertices? 5. How many edges? 8. Yeah, 1, 2, 3, 4, 5, 6, 7, 8. How many faces? 5. And just according to how Euler's, now that's Euler's formula. I don't know if I was pronouncing it right earlier. That's called Euler's formula. I don't know why. That's just how I said his name. According to Euler's formula, if I take the number of vertices, I minus the number of edges, and I add the number of faces, 5 for faces, then that should come out to 2. And sure enough, 5 minus 8 plus 5 gives you 2. Okay, so far the theory works. Middle column, Dakota, you should put your foot up. Okay, middle column, how many vertices? 12. How many edges? 18. How many faces? 8. Is it? Yeah, 8. Okay, and if you check vertices minus edges plus faces, sure enough, gives you 2. Okay? Last one, how many vertices?
6,
Thank you, Zach. How many edges?
12,
8. And if you check, 6 minus 12 plus 8 does equal 2, so it always works. Why does this matter? Because we're going to get into math problems like this. I would expect to see this problem on the quiz next week and the test the week after that. It's not on your paper though. A polyhedron has 18 vertices and 6 faces. How many edges are there? So I know I've got 18 vertices, so V equals 18. And I know I've got 6 faces, F equals 6. And the question is, how many edges are there? So I just plug it in the formula and go. V minus E plus F equals 2. So 18 minus, I'm looking for the edges, plus F is 6 equals 2. I'm going to solve it for F. So can you tell me what to do to get E by itself? I'm just solving for E. No, because they're on the same side of the equal sign, but I can go ahead and combine them. So 18 plus 6 makes 24. Okay. Now what? What has to move? No, the E is going to stay because we're trying to get the E by itself. Who moves away from the E? The 24. How do I move it? Subtract it. Okay, so now I have negative E, because that's been a negative E this whole time, equals negative 22. Now, I don't really want negative E, so technically I'm going to divide out a negative 1, which is going to make everything be positive now, so I'm flip the sign. So now I know that the edges are 22. There's 22 edges in the shape. So I didn't have to draw the shape. I didn't have to try to imagine it in my head. Just did the formula because I knew it was a polyhedron, so I could do Euler's formula. Questions at all? Okay. So they're calling this the Pythagorean theorem. It looks like the distance formula. So the Pythagorean theorem and the distance formula are the same thing. So what it does is, let's say you have a box and you need to know how far it is from, say, the front corner of the box to the opposite. So I'm going to go from the front top corner to the back bottom corner. Why might this be important? Well, I think that when you build cars, if you're planning on like rolling them like in a demo derby, I think you got to build in supports into your cars, and those are always diagonal supports. So you can go like from the front of the car to the back of the car. How long is that? How long is the piece of steel that I need to build? So anyway, you know, this diagonal piece going through here. Lucifer, wake up. Oriana, wake up. There we go. We're going to try and find out how long would this pencil be to have to connect these two opposite corners. That's what this distance formula is. So it says length squared plus width squared equals height squared, takes the square root of the whole thing. So if I have a rectangular prism with these dimensions, how long would it be to go from one corner, top back, to the opposite corner on the other side, bottom front? How long would that be? That's what I'm going to look for. So I use that new distance formula that I got. The D, which stands for, this line here is called the diagonal, so you can think of D as the diagonal. The D equals the square root of L squared plus W squared plus H squared. And the L and the W and the H, they're all interchangeable. It doesn't matter which one you plug in for which. So D equals the square root of 8 squared plus 6 squared plus 10 squared. And I would just put this straight into your calculator. I wouldn't try to step out squaring each of the numbers. I would just type square root sine 8 squared and then tell me what comes up.
Hey, can I grab some more?
I'm not gonna.
14.14. So that diagonal is 14.14 centimeters long. So what I learned is that this line here is 14.14 centimeters long. Okay. What if they give me, this time they told me this dimension is the length and the width, but I'm looking for the height. And this time they also told me how long the diagonal is. So now I know that the diagonal is 18 inches long. Well, it's still the same formula. Except for now I plug the numbers into different places. So, Ariana, do I have the D?
Yes.
And it is good. So now this time there's something on the left side of the equal sign. Equals the square root, and the L and the W can be the 8 and the 12. And the height is what I'm looking for, so it's going to stay H squared. I'm going to solve this. I'm going to go ahead and stick with Ariana because she didn't get to say much. Ariana, I want to get H by itself in the very end. Lead me through the process as much as you can. You want to put those together?
Yes.
Okay. So I've got 18 equals, and when I put 8 squared plus 12 squared, that ends up coming out to 208 because they're squared. So now I have 208 plus H squared. Now what? Cannot yet, because it's protected by the square root sign. Square it. Yeah, I'm going to do the opposite. I'm going to get rid of the square root sign by squaring, but I got to do it on both sides to keep everything even. 18 squared gives you 324. And all it did on the right side of the equal sign is it just erased the square root sign. It didn't change anything about the numbers. It just erased the square root sign. That's all it did. So now over here I still have the same numbers, just no square root sign. Okay, Ariana, now what? Now I can subtract it to move it over. And so now I get 116 equals, this is still H squared, so it equals H squared. And then, so H. Now I square root it to get rid of the exponent. So that's how I come up with that H equals, is it? Really? Okay. I thought it was 9.1. 10.8. Okay. Questions? Nelson, you good?
Isn't that your husband like that?
Yes.
That was so much
So now we're going to graph a cube with the edge length of 4 units and a vertex of 0, 0, 0. So to graph, now that we're doing 3D pictures, we're going to do, I guess just fine. Just go. Okay. Since we're doing 3D pictures, we need a 3D graph. Okay, so here's the graph that you originally have been used to graphing on ever since Algebra 1, and you've got the x-axis, you go from negative x's out to positive x's, you're going to have to label your graph because it's not labeled on your paper, so you're going to have to put the axis labels in there. And then you've got the y-axis, and you go from the negative y's up to the positive y's. Okay? And now you've got this third dimension. Okay, so we have the right, left, we've got the up, down, now we got to add the in and out dimension. So even though this line looks like it's going diagonally up and down, what it's really doing, what we're supposed to be representing, is that this part of the line from here to here is popping out of the page at you, okay? And then this back part of the line is going behind your paper, behind the active board. And we're going to call that the z-axis. So the part that's supposed to be popping out, even though it looks like it's going down, the part that's popping out, we're going to call those the positive z's. And the part that's going behind your paper, we're going to call those the negative z's. Sorry, that's the two axes. And remember how when we used to graph with just the x and the y, you had ordered pairs, and they looked like this. Well, now we've got what's called the ordered triple, and it goes x, y, z. So now it's points for the 3D plane, and these are called ordered triples, and ordered triple is what goes in at the top of your paper in the blank. So it's telling me I've got a cube, and one vertex, one corner of the cube, is at 0, 0, 0. That's a point. X, Y, Z is at 0, 0, 0, which is right here in the middle. I'm going to have to erase some stuff to make this look nice. Okay, so the first corner of the cube is right here. Cubes, if you were to count, you'd see that cubes have 8 corners. So we're going to plot 8 points to be the corners of the cube, and then we're going to connect the dots, and it's going to make a cube on our page. Okay? And everything's 4 units. So we're going 4 in all the different directions. Okay? So to figure out what the 8 different points are, I'm going to make every possible combination of 4s and 0s that I can. And coincidentally, there's 8 different combinations. So I've got, okay, I have 0, 0, 0. I already plotted that. So now I'm going to just add 1 4 to the mix. So I can go 4, 0, 0. I can go 0, 0, 4, 0. Or I can go 0, 0, 4. So that's 1/2 of my corners. Okay. And then the other half of my corners goes, if I start with 3 4s, I think my mouse is going bad. If I start with 3 4s, then I can add 1 0 to the mix. So I can go 0, 4, 4. I can go 4, 0, 4. Or I can go 4, 4, 0. So now I'm going to plot all these points. So we're going X, Y, Z. X, Y, Z. Already did 0, 0, 0. So 4, 0, 0 tells me to go positive 4 on the x-axis. That's 4 to the right. 1, 2, 3, 4. I don't go anywhere on the y-axis, and I don't go anywhere on the z-axis. So I just put my dot right there. 0, 4, 0 is saying I don't go anywhere on the x-axis. I go 4 up on the y-axis. 1, 2, 3, 4. And I don't go anywhere on the z-axis, so I put a dot there. And then 0, 0, 4 is saying don't go anywhere on the x-axis. Don't go anywhere on the y-axis. Just come out towards yourself 4 on the z-axis. So I'm going to come out 1, 2, 3, 4 on the z-axis. And put a dot there. So now I've got half the corners of my cube in place. Let's get the other half. 4, 4, 4. I'm going to go 4 to the right on the x-axis. 1, 2, 3, 4. And before I put a dot, I'm going to go 4 up on the right on the y-axis. 1, 2, 3, 4. And before I put a dot, I'm going to come towards myself 4 on the z-axis. So I'm sitting right about here right now. I'm going to come out 1, 2, 3, 4, and put my dot on the z-axis. 0, 4, 4, don't go anywhere on the x-axis. Just go 4 up on the y-axis, and then come out diagonally towards yourself 4 units. So out 1, 2, 3, 4, about to here. Okay. 4, 0, 4, go 4 right on the x-axis. Don't go anywhere on the y-axis. Come out 4 towards yourself on the z-axis. 1, 2, 3, 4. Okay. And then the last one, 4, 4, 0, just means I'm going to go right 4 on the x-axis, up 4 on the y-axis, and I'm not going to do anything with the z-axis because it's a 0. Now I have a ton of different dots. I'm going to connect them to form a cube. Look, here's the top of the cube. Here's the bottom of the cube. And here are the sides of the cube. Isn't that neat? Yes, it was. Well, 3D. Sometimes you may call it. You lost?
Yeah.
Where?
I don't know how to break it down.
Well, we'll catch up later, okay? Cubes are not going to be on your quiz or your test. I'm writing chapter 10. It's not going to be on the quiz or the test. But what are going to be on the quiz and the test are cones. So if you get lost, please say something to me before I get all the way to the end of the problem. Okay, a cone. We're going to do a cone. And we all know what cones look like. You got a circle at the bottom and then it goes up like that. Okay, you are going to have to know how to do this for the quiz and the test. Okay, the radius of the cone is 3. So from the center out to all the sides is 3. And if you look at your cone, you can see that the cone is going right and left for sure. So it's going to go on the x-axis, okay? And it's also coming towards you and it's going away from you. That's the bottom of the cone. It's coming towards you and going away from you. So this circle of the cone is going to use up the x-axis and it's also going to use the z-axis for the circle. And I have a radius of 3. So from the middle of the cone, because it's centered at 0, 0, 0, from the middle of the cone, I'm going to go right 3. I'm going to go left 3. I'm going to go towards myself 3. And I'm going to go away from myself 3. So these 4 dots that I just put are showing you where the bottom circle of the cone is going to be. I want everybody to catch up to this point. Is anybody lost? Because that's for the height. We're just doing the bottom right now. We're just doing the base of the cone, this little circle down here, and it just goes left and right and towards you and away from you. Okay, so connect those dots to make the circle. Okay. And now we're ready to do the height of the cone. And it tells us in the story that the height is 5. So that's going to be going up 5. So from the bottom of the cone up, 1, 2, 3, 4, 5. Here's the top of the cone. And to indicate that this is a cone, I just artistically draw in some little connectors from the top of the cone down to the bottom to indicate that this should look like a cone. Thank you.
Better than mine.
This is the 5th time I've made this cone. Questions?
Mine looks like that ice cream.
That ice cream. But it still looks like a cone, right?
Yeah, that's two cones.
The last thing we're going to talk about is the distance formula and the midpoint formula. Okay, you guys already know how to do this. You've seen the distance formula before, finding the length between 2 points. So far we've only done it with the x's and the y's. Now we're adding to it the third dimension, the z. And you've seen the midpoint formula, finding the exact center between 2 points. You saw it with the x's and the y's, and now we're just adding in the z. So find the distance between the 2 points. Okay, so here's your 2 points. You've got x1, y1, and z1. And then you've got x2, y2, and z2. So to find the distance, to find out how far apart they are, you use your distance formula. Okay, so x2 minus x1 squared. I wonder if this pen would work better. Plus y2 minus y1 squared plus z2 minus z1 squared. Good.
Go ahead.
No. Okay, so then you just fill it in. x2 is 2, so 2 minus x1, 2 minus 0 squared, plus, and then the y, 8 minus 0, 8 minus 0 squared, and then the z is 5 minus 0 squared, and all this is under the square root sign. Type it into your calculator exactly how you see it. Don't try to step anything out, just type it in. The square root button, then the parentheses button, then the 2 button, and you keep going until you get to the end where you hit enter, and it tells you that this line is 9.64. That's right, it's 9.64 long. So that's how long the line is. And now we need to find where is the location, where is the point, what's the coordinate for the point that's in the exact middle. So that's the midpoint. Remember, the midpoint would be like x2 plus x1 over 2. So you add up the x's, the 0 and the 2. 0 plus 2 divided by 2 gives you, gives you 1. Okay, and then you add up the y, 0 plus 8. 0 plus 8 divided by 2 gives you 4. Okay, and then you add up the z's, 0 plus 5 divided by 2 gives you 2.5. So where is the midpoint between this point and that point? It's at 1, comma, 4, comma, 2.5.